We're going to continue on here with chapter 11. And we were talking about electron configuration. Remember, electron configuration is basically the order at which the electrons go into the atom. There's a specific order at which they do go in, which was that zigzag sort of thing that we talked about last time. That will give you the correct order. Our electrons are housed in different types of orbitals, as we talked about. There are s orbitals, which could hold a maximum of 2 electrons. There are p subshell, which is made up of 3 different p orbitals that could hold a maximum of 6 electrons. There are d subshell, which is made up of 5 individual d orbitals, which could hold basically 10 total electrons if you fill them all up. And there's f orbitals, which there are 7 f orbitals. And if we filled up the f subshell, we could put in there basically 14. So let's take a look at argon. I think we did chlorine there to close out last time. Argon, which is 18, and the electron configuration would be 1s2, 2s2, 2p6, 3s2, and 3p6. Remember that the first number that we see is really the energy level. So when we look at the 1 and the 1s, that means we're on the first energy level. The s is the type of orbital, and the numbers on top are how many electrons there are in each of the orbitals or subshells that we fill. We simply just count up the top numbers. We're up to 18, which means we have successfully filled them up. In this case, we have 2 electrons on the first energy level. We have 8 electrons on the second energy level. And on our third energy level here, we have 8 more electrons that are present. We also talked about drawing what is referred to as the orbital diagram. And remember, the orbital diagram are really boxes, are lines, where each one represents sort of an orbital. And where they go in, they do go in upwards first. The second electron comes in, as we talked about, in what's referred to as the paired orientation, which has a reverse spin of it. And that is how they do fill. As we talked about, when we have multiple orbitals within a subshell, they actually fill parallel first. So each individual orbital in the subshell gets an electron. Then they come back and pair up. So if we were going to fill our p's, again, each one gets one, then they pair up. Then obviously we continue our pattern here one at a time and pairing up at that point. This is obviously not drawn correctly in terms of energy, just to save room on the page. But obviously the 3p orbitals are higher in energy, further away from the nucleus than the 1s orbital is. Any questions on that there? Remember, if you know pretty much the total number of electrons you could put into s, p, d, and f, and you know the zigzag thing that we talked about, which is something you can create really quickly for yourself. Remember that it's on the first energy level that s's appear. It's not until you get to the second energy level that p's appear, not until the third energy level that d's appear, and not until the fourth energy level that f orbitals appear. And if you just start with that, you basically just fill in the numbers underneath, and you can recreate if I wrote the letters right there, that would be S's there in that first column there. There we go. S's. Then these are P's. And these are D's. And those are F's. Thank you. And again, remember, we always start this way. And that will get you your correct order as you do that. If you don't screw it up and really butcher the letters like I just did there. Any questions on that stuff we talked about last time? Okay. All right. So another sort of principle, we talked about the idea of Hund's rule and all that is what's sometimes referred to as the off-ball principle. It's based on the idea that basically protons are put into the atom basically one at a time. And that is basically the idea of electrons as well. They do go into the atom basically one at a time. As we also talked about, they go in lowest energy and then go to the next lowest and the next lowest. And they sort of build from the lowest energy, which is closer to the nucleus, and build up as they sort of fill in all their electrons. A reminder as well that you do not have to necessarily fill in a particular orbital or subshell, but you just need to distribute your electrons correctly. Now, we and most chemistry classes that you take write electron configuration like we did with that order, and that is what is sometimes referred to as the filling order, how the electrons go into the atom. You'll occasionally sometimes see around electron configuration looks slightly different, where all the energy is basically the same for everybody, and it kind of goes in order, all the threes first, all the fours next. And that's really based on energy, and most people don't write electron configuration based on that. So based on filling order, which is what we've been doing, is basically how you write electron configuration, and you should write electron configuration. The major change, as we talked about, remember, right, is that basically in the filling order, the 4s orbital is less energy than the 3D. So we do get electrons here first, followed by the 3D, and that gives you the proper sort of filling order. As we'll talk about maybe in just a second, there's actually a weird thing that happens. These guys actually do switch in energy when you start putting electrons in the d orbital, and it ends up being actually the s is actually a little bit higher in energy than the d. But filling order, s is lower than d, and they should get them first, which if you follow our little guy there, he should end up. We look at the next one, which is potassium. Basically, we got 19, so that's going to take us to 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. If we look at the electron configuration up through here, that is 18 electrons. And if we look at the periodic table for 18 electrons is argon. So sometimes when we write electron configuration, we can kind of do a shorthand for electron configuration, and is sometimes referred to as the noble gas configuration. And basically what we do is we take the noble gas that comes right before whatever element we're writing the electron configuration for, and we basically put it in brackets to indicate the electron configuration for what we see here in the box. And then we just continue on with the electron configuration, and it's what is referred to as sometimes noble gas configuration, sort of a shorthand that sometimes people will write when they are doing electron configuration. A key though is it does need to be a noble gas that's in the bracket. So you got to start with the noble gas that comes right before it on the periodic table, and then you can continue on with the electron configuration. So if we looked at magnesium, for example, which is 12, the noble gas that comes right before magnesium on the periodic table is actually neon, which is 10. And then we can continue on with the configuration, which would be 3s2. So that would be sort of a shorthand way that you could write the electron configuration for something, for example, like magnesium. Again, you could do it for anybody on the right-hand side as well. Non-metals, again, you still have to back up. So, you know, if you were doing something like chlorine that we did earlier, which was 17, you would have to all the way back up there, also back to neon, which is 10. And then you would have to continue on with 3s2 and 3p5. So you would, again, have to go all the way back to that noble gas. You can't go forward, obviously, because then you have too much electrons, obviously, right? So you got to go backwards to noble gas and then build from that point. So that, again, is sort of a shorthand way that you could express electron configuration. Again, sometimes referred to as noble gas configuration. Any questions on that there? Now, transition metals are a little bit different. They do get into actually the d orbitals. Our first row transition metals number, they're 21 on the periodic table. And remember that actually is where 3D starts. And if we get into our electron configuration, there are a couple of exceptions. Actually, there's a lot of exceptions in the transition metal region in terms of normal electron configuration. For example, if we looked at chromium, which is 24, and we wrote the electron configuration, you know, if we just followed our zigzag, it'd be 1s2, 2s2, 2p6. If we wrote it all the way out, 3s2, 3p6. And if you follow the normal sort of way you would do it, you would write 4s2 next and 3d4 if you followed this kind of zigzag thing that we were talking about. There is an exception for chromium and copper as well. It's been found experimentally that actually they're right about here, there's an extra electron up in the d orbital, one less electron in the s orbital, and the ending should actually be, we'll come this way, like it shows down there on the bottom, 4s1, 3d5. If you think about it, by sort of promoting that electron up, you're now putting a single electron into each of the d orbitals, all in the parallel position, right? Which creates a nice sort of stable situation for it. A very similar exception happens with copper. It's 29. It actually, again, has one more electron up in the d orbital, one less electron in the s orbital. They're actually able to do that pretty simply because they are extremely close in energy. So when we look at that 4s orbitals and we look at the 3d orbitals to begin with, they're very, very close. So it doesn't take a lot for an electron to kind of pop up to a higher energy level. And as I talked about before, as we start putting electrons into the actual d orbitals, there's actually a switch in energy that occurs. And what ends up happening actually is the 4s actually ends up being higher in energy. And that's after the electrons start going into the 3d orbital. So there's some very closeness in terms of those orbitals. And actually, as they start filling, there's actually a switch in the overall energy as to where those electrons go. That's really important in terms of, as we'll talk about here in just a second, transition metals. When they lose electrons, they actually lose sort of a different sort of electrons because of that energy switch that occurs. So for us, chromium and copper are the two that you should be aware of in terms of exceptions to the normal electron configuration. Reality, and when you take 1A, you'll probably learn a lot more. But if you look at where chromium and copper is on the periodic table, kind of come down and over, there is a ton of exceptions. Silver is an exception. PD is an exception. In fact, I think PD doesn't have any electrons in the S. They've all moved up to the D. So there's a lot of exceptions kind of below chromium and copper on the periodic table in that transition metal region. But for us, you'll just be responsible for these two. Everything else, even though technically speaking, it is an exception, you could write based on the zigzag thing. But just keep in mind, in reality, a lot of exceptions sort of in that region of the transition metal. Any questions on that there? The Lanthanites series, which are those guys on the bottom, that again is where we get really into our Fs, where our two rows on the very bottom periodic table, those are really where the electrons sort of fill in those f orbitals, starting on the 4th energy level. And again, here you might be able to see some of the exceptions. As you can see here, as I said, platinum, our PD there has no S's. And again, a lot of very similar exceptions to the periodic table as you kind of go through it. So let's talk a little bit about the periodic table actually and electron configuration. You can actually count off electron configuration from the periodic table if you know what you're doing. When we look at group 1 and 2 on the periodic table, those are our S block because there's 2 electrons right in the S orbital. From group 3 to 8 is our P block because there are 6 spaces there and you can put 6 electrons in the P subshell. The transition metal in the middle here are our Ds because there are 10 spots there, which you can put 10 electrons in there, and our 2 rows on the bottom, which is our Lanthanites and Actinide series. You can basically put your F electrons there, which are 14 spaces if you count it. So for example, if we looked at sodium, which is hanging out right about here, we could actually use the period numbers there as our sort of energy levels. So starting up at the very top here, if we went all the way across, that would be 1s2. Coming this way, that would be 2s2. That would be 2p6. And then we would stop right here at sodium, which would be 3s1. So you literally could count off the electron configuration if you wanted to from the periodic table. If we looked at chlorine, which we also did, which is somewhere around here, We would continue on, starting at the top again, 1s2, 2s2, 2p6. Now we would go all the way across here, 3s2, and then we just simply count here, 3p1, 2, 3, 4, and 5 would give us our 3p5 that we got. You do have to be really careful because right about here, these are the d orbitals, which again begin on the third energy level, but they are on period 4. So they actually are one behind the period number. And like we maybe went to iron, which is right here. We were going to count off the electron configuration there for iron. We would again start at the top, 1s2 going all the way across, 2s2, 2p6 to the end, 3s2, 3p6. Again here, 4s2, but the importance is this is now 3d right here, and that's 3d1, 3d2, 3d3, 3d4, 3d5, and 3d6, and they would be there at the periodic table. The other thing you have to watch out for is down here, these two rows, as we talked about, technically go here, and this is 4f and 5f, which are actually 2 behind the period number. So it gets a little crazy there in the middle. You got to be careful what you're doing. I personally would recommend doing the zigzag stuff that we've been doing. You should never screw up if you follow that. If you count it off the periodic table, you might screw up, especially when you get into the transition metal region. But if you want, you could definitely count out the electron configuration. You just got to be careful at those two spots where the D's come in and obviously where the F's come in as well. Any questions on that there? So any question on electron configuration there? We also talked about obviously electron configuration with stuff that's been really neutral, but what happens when we do have ions in electron configuration? Let's talk a little bit about what we need to do with those. If we have ions, which obviously are things that have charges, let's just say we had oxygen. Oxygen with no charge is 8 electrons, which means its configuration would be 1s2, 2s2, 2p4. When oxygen does gain a charge, it becomes a -2 charge, which means it has how many electrons? It does have 10 electrons in this case, which means you do need to adjust the electron configuration to 1s2, 2s2, 2p6. If we look at something like aluminum, which is 13 with no charge, which means it has 1s2, 2s2, 2p6, 3s2, and 3p1. When aluminum gains a charge, it does gain a +3 charge, which means aluminum would also have here 10 electrons, right? Positive means we lost electrons, 3 electrons are lost. And that means it would have a 1s2, 2s2, 2p6 configuration. That means really when we look at oxygen with a -2 charge, it is the same electron configuration as neon, right? Aluminum is also the same electron configuration as neon when it has a +3 charge. And obviously neon has the same electron configuration as all those. All three of those things, oxygen with a -2 charge, aluminum with a +3 charge, and neon all have the same electron configuration. That means that they are what are referred to as being isoelectronic with each other. Basically, this configuration. By the way, neon is what element on the periodic table? That is a noble gas. And as we'll talk about in the next chapter, that is really the basis of all bonding. The basis of all bonding, be it ionic bonding, be it covalent bonding, where they share electrons, is for everybody basically to end up with the same number of electrons as a noble gas. Noble gases are extremely stable. They're chemically inert. Is the goal basically of everybody basically to get to the same electron configuration as a noble gas. The way metals do it is they lose electrons when they make an ionic compound and they back up to the noble gas that comes right before them. How nonmetals do it is they pick up electrons and they go forward to the noble gas that comes after them. And that's the basis of ionic bonding, losing electrons, gaining electrons. Both of those guys do that. So they both achieve that noble gas configuration. And it really is the basis of all bonding. Any questions on that there? So anything that has a charge, you do need to adjust, and you do need to adjust it based on the total number of electrons. And if it is a representative element, anybody on the left-hand side of the periodic table, really right-hand side of the periodic table, when they lose or gain electrons, they should end up in a noble gas configuration. Basically, they should end up with the same electron configuration. Now, transition metals are different. When transition metals lose electrons, it's a little bit different. So let's talk a little bit about transition metals and they lose electrons. As we talked about just a second ago, when transition metals put electrons in, they do go into the s electrons first, and then they do go into the d electrons next. As I talked about a second ago, there is a switch in energy that occurs when this happens. And we end up with those 4s electrons actually being highest in energy than our 3d. So when electrons really lose, when atoms really lose electrons, they really lose their highest energy electrons. And those are sometimes referred to as valence electrons. So when transition metals basically will lose electrons, they will always lose their s electrons first, because there's always that change in energy that occurs, and those s electrons end up actually being higher in energy than the d. So for example, if we looked at iron, like we just kind of read off the periodic table there as configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. What happens when iron loses 2 electrons? It goes from obviously here 26 electrons down to 24 electrons. And what ends up happening because of the switch in energy, the iron will actually lose these electrons right here first. There's 2 electrons there. They will actually be lost. And we would end up with a 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 as the proper electron configuration for iron with a +2 charge. Here again, we actually lost the second to the last ones that were filled, which are the s's. Or if you wanted to, this would be argon 3d6 in this particular case. Now, what happens if iron, because it is a transition metal, has the ability actually to make different charges, so it can actually make a +3 charge. What happens when it goes to +3 is it now needs 23 electrons, right? One more loss. So the same thing is going to happen. It's going to first take out those 4s2 electrons, but at this point, pretty much we just took those out. The next highest in energy would then be the 3d, and it would dip into the 3d here and take one of those electrons out to give the grand total of 3 electrons that were lost, and that would give us a 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 are argon 3d5. So transition metals are a little bit different in terms of the electrons that are lost. Every single transition metal, no matter which row it's on, will always lose those s's first, because group 1 and 2 are the s's. So they basically lose those electrons first. Then if they need, they will dip into the d orbitals there to lose the remainder of the electrons at that point. Representative elements, like we did before these, pretty easy. It's pretty much the last ones you write in the electron configuration are the ones that are lost. Transition metals, they're kind of the s's first, and then the last ones that are written in the configuration. Any questions on that there? Why don't we try, let's try, why don't we do calcium with a +2 charge? Why don't you write the electron configuration for that? Why don't we do nickel with a +4 charge? And why don't we do phosphorus with a -3 charge? Neutral guy is 20, the atomic number. Neutral nickel is 28. And neutral phosphorus there is 15. All right, take a second, write the proper electron configuration for these guys here. Look, so starting with calcium, it has a +2 charge, which basically means it's going to end up with 18 electrons. Again, if we wrote out the electron configuration for calcium with no charge, it would look something like this. When it loses the 2 electrons, it will be the last ones that are written here, which gives us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, which is 18 electrons, and also the same electron configuration as argon, right? So again, here calcium loses the 2 electrons. It backs up to the noble gas that comes right before it. It's now sitting with the very good stable electron configuration, just like argon in this particular case. Any questions on that there? Okay, looking at nickel with a +4 charge means that it is going to actually end up with 24 electrons. Again, if we write nickel's configuration without a charge, 1s2, 2s2, 2p6, 3s2, 3p6, then we're going to go 4s2, 3d8. In this case, we need to dump 4 electrons. Because nickel is a transition metal, we know for sure it's going to always lose these 2 here first. Problem in this case, it's only 2 electrons. That means we still need to lose 2 more electrons. Because it's a transition metal, we will then come out to here to take our next 2 electrons out of, and we will end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And if we count up the top there, 6, 2, 8, 10, 12, 18, 18 and 6 is 24. This would be the correct electron configuration for nickel that has a +4 charge. You also could do the argon 3d6 if you'd like to kind of shorten it down a little bit in this particular case. We also see here with this one and the one when we looked at iron, the transition metals actually do not end up all the way back to a noble gas configuration because they have those d electrons. So they come to a much more stable situation, but they do not actually end up backwards to the noble gas. It's just the representative elements. And 1, 2, 3, 4, 5, 6, and 7 basically will end up in noble gas configuration. Transition metals will not. Phosphorus, which has 15 electrons with a -3 charge, means it gained 3 electrons. We'll put it to 18 electrons. And in this particular case, will take us to 1s2, 2s2, 2p6, 3s2. Again, before we did it here, we had 3p3. The 3 electrons will be gained into our p subshell as it has room for it. And once it becomes a -3 charge, 1s2, 2s2, 2p6, 3s2, and 3p6, with those electrons going in there, which also gets us to argon's configuration. So again, in this case, our negatively charged guy goes forward, gaining those electrons, and becomes much more of a stable situation. Any questions on electron configuration, charges, no charges, transition metals, charges, no charges? You need to obviously know how to write the electron configuration for everything. You need to be able to draw the orbital diagram with the boxes, the arrows, and all that kind of stuff. And obviously things with charges and no charges. Any questions? Okay. Yeah. All right, let's talk a little bit about some finishing here of the periodic table and some of the stuff that we talked about with electron configuration. First off, the highest energy electrons are what are referred to as the valence electrons. They are the ones in the highest energy levels, furthest away from the nucleus. The importance of valence electrons are they're really the ones that are involved in bonding. So when we talk about bonding, it does make sense. Highest energy, furthest away from the nucleus, which means when multiple atoms come together, or pretty much those outside electrons are the first ones to say hello to each other. They're also furthest away from the nucleus, which means they're not held as tightly and they're easier to remove. So if we look at nitrogen, for example, nitrogen has 1s2, 2s2, 2p3. In this case, the 2 means it's on the second energy level. So in terms of nitrogen, these 5 electrons here are the valence electrons. They're the ones in the highest energy level. And nitrogen would have 5 valence electrons. If we looked at sodium, which was 11, 1s2, 2s2, 2p6, 3s1. It is the 3s1 here, which is the highest in energy, which means sodium would have 1 valence electron. You can figure out the number of valence electrons from writing the electron configuration, but who wants to do that? We don't have all day usually. So we could look at the periodic table and actually figure out the number of valence electrons. The number of valence electrons equals the group number. So if we look on the periodic table, sodium is group 1. It has 1 valence electron. Nitrogen is group 5 on the periodic table, has 5 valence electrons. That is a much faster way of doing it. If we looked at our phosphorus, would also have 5 valence electrons. We did oxygen earlier, which was 1s2, 2s2, 2p4. Oxygen is group number 6, and that is its 6 valence electrons. So you could write out the number of valence electrons or the electron configuration to figure out the valence electrons, but much, much faster is basically the group number equals the number of valence electrons. Transition metals are a little iffy, if you will. But the good news is we won't do much with bonding and having to worry about valence electrons. But for the most part, for transition metals, most people, a lot of people will say they have 2 valence electrons, which is those S group there that we were talking about earlier, that get lost first. Some people could say that they could have upwards of 12 because after we go through the S, we then went to the D. So they technically could have a lot of things. So good news is we won't work too much on that. We'll call it 2 valence electrons for the transition metals, but they could have upwards of 12 because technically you go into the D. The good news is for the representative elements, group 1 through 8 that we talked about with the periodic table, group number will equal the number of valence electrons. That means chlorine should have how many valence electrons? Should have 7, right? And if you wrote out the electron configuration or looked at the one we did earlier, it would have 7 in those highest energy levels. Any questions on that there? All right. So as I mentioned, we have our 7 valence electrons for fluorine, chlorine, and carbon there, group 4. Again, if you wrote out the configuration, would have 4 valence electrons. We'll talk a little bit about some of these periodic trends, and some of this we got into when we did that experiment way ago. Metals and non-metals. As you go down a group, especially the metals, they do give up their electrons a lot easier. So if you go down group 1, cesium is much easier to give up the electrons than lithium. And we also saw that when we did that experiment, if you remember watching those videos, right? Reactivity really started to increase as you went down group 1, right? With those metals when they added it to water, right? And it started to explode and catch on fire and stuff like that. Most active nonmetals are found in the upper right of the periodic table, which is also something we saw in that experiment, right? Going up group 7 there, iodine, bromine, chlorine, and then fluorine being the most sort of reactive going upper on the periodic table. So let's talk a little bit about why that is. One of the reasons why we do see that is this periodic trend. Periodic trend is known as ionization energy. Ionization energy is the energy that's required to remove an electron in its gas phase. The higher the ionization energy, the harder it is to remove an electron. The lower the ionization energy, the easier it is to remove an electron. Electrons, by the way, do come off. They do come off actually one at a time. So sometimes people think they just all pop off at once. They actually do pop off, for example, one at a time. So for example, if we were looking at something like magnesium, the first thing that would happen is magnesium would lose an electron. And we would put the electron on the right-hand side of the arrow to indicate that it is coming off. When it does so, the magnesium will actually gain a +1 charge at that point. The next thing that happens is the magnesium with a +1 charge will then lose another electron, also on the product side. There is an ionization for each electron that comes off. This is what's known as the first ionization energy. This is what is referred to as the second ionization energy. Is it easier to remove the first electron or the second electron? Which one's easier? It is easier to remove the first electron. Yeah. When you remove the first electron, what happens to the overall size of it? Does it get larger or smaller? It gets smaller, right? Electron cloud gets smaller, right? Which means even our furthest electrons are now closer to the nucleus, right? When I want to try to pull off the second one. So that second electron now has moved closer to nucleus, going to take a lot more energy to do that. And if you look at the ionization energy values, you will actually see a big jump in terms of the ionization energy when you try to go from the first electron to the second. And then what happens, for example, if this magnesium with a +2 then decides I want to lose another electron? We would expect the ionization energy to also jump a lot higher. Now, does this happen, for example, for something known as magnesium? If we look at the electron configuration, 1s2, 2s2, 2p6, 3s2. Magnesium has how many valence electrons? 2, right? It's group 2. It is these guys right here. These are the valence electrons. The electrons that are not valence electrons, which are closer to the nucleus, they are sometimes referred to as core electrons, which means they're super close to the nucleus to begin with, and they're getting closer to the nucleus as we continue to lose these electrons, which means in the case of something like magnesium, it just doesn't happen. If you were actually to look at the numbers, it's maybe like a 20-fold difference in terms of energy to try to rip off that third one. As soon as you go away from your valence electrons, which are the outermost, not really held as tightly, you get into those core electrons. You typically are just way too much energy to try to rip those electrons out. They basically will not happen. That's why magnesium will only get to a +2 charge ever. Also the same, look at something like sodium, which is 11, 1s2, 2s2, 2p6, 3s1. Sodium has 1 valence electron. And as soon as you get rid of that one, you're now into these core electrons, which the amount of energy is enormous compared to just trying to remove that first one. And that's why something like sodium will only form a +1 charge. So that's why there's certain things on the periodic table that have sort of fixed charges. And it has to do with sort of the electrons, for example, that get pulled off and not pulled off. Any questions on that there? So while we're talking about that, the general trend in ionization energy, first ionization energy, which is energy to remove an electron, is it increases as you go up and to the right and decreases as you go down and left on the periodic table. And since we're talking about things with charges, everybody in group 1 on the periodic table will form a +1 charge. Everybody in group 2 on the periodic table, when they do form a charge, will be +3 or +2. Right around here, we have that staircase in group 3. It will be +3, which is usually aluminum. We do skip the transition metals, which are here. Group 4, no real good pattern. Group 5, and we're talking non-metals up on top, will form a -3. Group 6 will go -2, and group 7 will go -1. And again, those are all non-metals, which are typically the guys that will gain electrons. For the most part, the transition metal region, which is in this region here, they could have multiple types of charges. There are a few exceptions. The few exceptions are zinc and cadmium. When they do form a charge, they have fixed charges of +2. And if you hang a left there at cadmium where silver is at, it is +1. So these are some guys that have fixed charges on the periodic table. Everybody else pretty much has a variable type of charge. They can make type charges, which is pretty much our transition metals. And really below the staircase here, where we have things like lead, antimony, tin, those guys could have multiple types of positive charges. When we talk about ionization energy, because it is the thing to lose electrons, we're really talking about cation formation here, right? Those are guys that become positively charged. And again, up to the right, higher, left and down, lower. Any questions on that there? Let's talk a little bit about atomic size. As we go up and to the right of the periodic table, everybody gets smaller. Again, as you go up and to the right, we have electrons, and everybody gets squeezed into positive charge of that nucleus. The overall size of everybody gets smaller. As you go left and down, we have a lot more electrons, which are further away from the nucleus. They're not held as tightly, so it creates a much larger electron cloud, and we have a much larger guy going that way. Another couple of important periodic trends is what is known as electron affinity. Electron affinity is the energy change that occurs when an atom gains electrons. So when something gains electrons, that's like anions being formed, right? Those are negative guys. When we look at the periodic table, it increases as you go up and to the right and decreases as you go down. So ionization energy, we talk about in sort of the formation of cations when they lose electrons. Electron affinity is when somebody gains electrons. By the way, if we were to show that, chlorine would gain an electron and become a negatively charged. So this is how you would display that. Electron on the reactant side or left-hand side of the arrow. When somebody gains, somebody loses, like we saw with magnesium. Right-hand side of the arrow is where you put the electron there. Another important one, which sounds very similar to what I just wrote there, but actually is a little bit different, is what is known as electronegativity, which we'll talk about in the next chapter as well. Electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Also increases as you go right on the periodic table, decreases as you go down. The most electronegative element you could have is actually fluorine. So electronegativity is really when an atom's like, I want your electrons, and it has high electronegativity. It's like, I'm just going to take your electrons, basically. I want to grab them. I want to take them. Somebody has low electronegativity. They're like, you can take my electrons. I'm not really interested in yours either. Go ahead, take them. Not a big deal. So all these are periodic trends, which help us understand really two main aspects of what we see when we look at the periodic table and what is happening in terms of metals and nonmetals. And let's just kind of put them all together here on our wonderfully drawn periodic table, also known as a big box. When we go up and to the right, we have high ionization energy and lower ionization energy as you go down and to the left. When you go up and to the right, we have a smaller size and increases as you go left and down. As we go this way, up and right, it is higher electron affinity. And when we go left and down, a decrease in electron affinity. And lastly, when we go up and to the right, we have an increase in electronegativity and a decrease in electronegativity as we go down. So what does all these things have in common, and why? What do we see on the periodic table? Basically, when we go up and to the right on the periodic table, we have that are overall much smaller because they have a larger positive charge, brings out even the furthest electrons closer to the nucleus, which means they're closer to the positive charge. That means that it's going to take a lot more energy to try to remove an electron from somebody up and to the right, because all those electrons, even the outer ones, are closer and held tighter. They also have a very high electron affinity, which means they much rather gain electrons than lose electrons. And lastly, they have a very high electronegativity, which also means in addition to wanting to gain electrons and hold on to theirs, they're going to want to take somebody else's electrons. So all those things come together with what we know upper right of the periodic table, which is our nonmetals. They typically like to gain electrons and become negatively charged. The opposite is true if we go left and down on the periodic table. We have atoms which are larger in size, which means the outer electrons are further away from the nucleus. They're not held as tightly, which means you don't have to put a lot of energy to remove electrons. And they really have no electron affinity. They're not interested really in gaining electrons. And they have low electronegativity, which means they don't want to gain electrons, nor are they interested in taking anybody else's electrons. So because of that, much larger electrons further away from the nucleus, not held as tightly, means that when we get to metals on the periodic table, they typically like to lose electrons and become positively charged. Any question on those periodic trends there? By the way, we talked about what happens when somebody loses an electron, they get smaller. When somebody gains the electron, what happens to their overall? Larger, right? They gain electrons, electron cloud gets larger. So when somebody meets an anion, it is a larger ion in terms of size than the neutral guy. And when somebody becomes a cation, they become smaller than their neutral sort of counterpart. Any questions on any of that stuff there? All right, so I think that should wrap up this chapter, I think. Yep. Okay, we're off to chapter 12 and bonding in this particular chapter. So we're going to kind of touch upon where we came from here with electron configuration. As we've been talking about, electrons are really important in terms of bonding. Those valence electrons are super important in bonding. And really, we just talked about really the ultimate goal of bonding is for everybody to achieve noble gas configuration. Is basically the ultimate goal. And let's talk about bonding here. First off, one way that we represent bonding is to use what are sometimes referred to as Lewis dot symbols, or sometimes just generically called electron dot symbols. And basically, because it's only the valence electrons involved in bonding, we represent valence electrons in Lewis dot symbols with a dot, one dot for each valence electron that's present. And again, as we just talked about, this super easy way to figure out number of electrons is the group number is really the fastest way to do that. So for example, if we looked at sodium, we would use the symbol, and basically we would use one dot to represent the one valence electron that is involved in bonding with sodium. Obviously, sodium has 10 more electrons, which are not usually pictured in these things. Just obviously the electrons involved in bonding are pictured. So typically we kind of use the symbol and again, a dot for each valence electron. So symbol, is there any rules? There's really no rules. Most people will kind of go around and then maybe pair them up, but there really is no rule except for one major rule, I guess, which is no more than 2 electrons per side is typically the deal. No more 2 dots per side. That means we have 4 sides and 2 dots. That's a grand total of how many electrons? That's 8 valence electrons. Who on the periodic table? Noble gases. So again, this is sort of the goal here as we're talking about here to sort of fill everybody up. So if we were to draw them here, you can see again, everybody here in group 1 has 1. Everybody in group 2 has 2, 3, 4, 5, 6. One notable exception is helium. Helium is a member of group 8. But it only has 2 total electrons, which means it can't have any more than that, obviously. So it obviously has 2 valence electrons. But everybody else there in group 8 obviously has 8 valence electrons. And as we were just talking about, the goal, for example, like phosphorus, is to move ahead to kind of fill up and end up with that same electron configuration as we see with argon. So let's talk about really 2 types of bonding we're going to talk about. And one is ionic bond. And in an ionic bond, it is always between a metal and a non-metal. And pretty much because of those periodic trends we just talked about, which one's going to lose electrons? It is going to be the metal that will lay up electrons over there to the non-metal. We're going to get a complete transfer of electrons that are going to occur here. And that's going to result in our metal becoming positively charged and a cation, and our non-metal becoming an anion and negatively charged. And there is absolutely 100% no sharing of electrons here. There has been a complete transfer of electrons. What holds that together is the opposites attract here. So the positive charge of the cation is attracted to the negative charge of the anion, and that is what basically holds that bond together. Absolutely no sharing of electrons, what is sometimes referred to as electrostatic attraction. No sharing of electrons here. The other type of bonding that we'll talk about is really like a covalent bond. And this is always between usually two nonmetals coming together. And the reason for that is, as we just talked about as well, if you look at where the nonmetals are on the periodic table, they're all pretty much sandwiched together in the same location, which means they have very similar periodic trends. And basically nonmetals in general don't like to give up electrons, but want to gain electrons, as we just talked about. So what happens when we put two nonmetals together is the best they could do is like, I'm not giving up my electron, I'm not giving up your electron. We will share electrons. So they basically will end up sharing electrons. And that's basically what happens here in a covalent bond is we actually get sharing of electrons. And as we'll talk about, sometimes the sharing is equal and sometimes the sharing is very unequal, but there's some aspect of sharing that occurs when we have a covalent bond that occurs. We get no aspect of sharing in an ionic bond. And that's because also, if you look at the periodic table, left-hand side metals, upper right-hand side non-metals, they have very, very different and opposite periodic trends that we just talked about, which means our metals will want to give up their electrons and our non-metals will want to gain those electrons. So in general, things with low ionization energy, which means you don't have to put a lot of energy in there to remove electrons, will become positively charged. Those with high electron affinities will typically tend to sort of gain electrons and become negatively charged. Any questions on that? All right. So general, as we talked about, basically everybody there in group 1 and 2 and 3 for the most part, which is aluminum, will form positive charge, and those anions upper right of the periodic table. So let's take a look at an example like lithium fluoride. If we take lithium fluoride and we write the electron configuration for each of them, we can basically illustrate the bonding that's occurring here by using Lewis dot symbols. So lithium, which is group 1, tells us that we should have Li with a dot. And again, he has a configuration of 1s2, 2s1. That's going to come together with fluorine, which is group number 7, which means it should have 7 dots. And an electron configuration 1s2, 2s2, 2p5. When these two guys come together, because of their size and place on the periodic table, what's going to end up happening is lithium is going to go, take my electron, please. The fluorine is going to say, thank you very much, and pick up the electron. By the way, it is at that point, the lithium does not have a charge to begin with. It is at that point that the lithium will then gain a charge of +1. The fluorine will then pick up that electron and fill out its electrons there, also gaining a -1 charge. It is that attraction between the +1 and the -1 that holds that together. There's absolutely no sharing of electrons, which is why when we draw it, we include the charges to indicate that there's no sharing of electrons. There's been transfer of electrons. Also, some people will put brackets around both, but some people will put brackets at least around the -1 to indicate, again, no sharing of electrons that are there. What happens more importantly when we look at the electron configuration is our lithium will then ditch its one valence electron, which is right here. It will end up with an electron configuration of 1s2 when it loses an electron. Who has 2 electrons on the periodic table? That is helium, which is a noble gas. Fluorine will take that one electron and stick it right there in the p subshell, and it will end up with a configuration of 1s2, 2s2, 2p6. That is 6, 2, and 2, which is 10. And it ends up with the same electron configuration as neon. So here in making this ionic compound, the lithium ditches his electron, backs up to the same electron configuration as helium, a noble gas, which makes it really stable. The fluorine takes that electron, moves forward in terms of its electron configuration to neon. They both end up with the exact same electron configuration as those noble gases, making it very stable for both of them and make them really happy and keeping that unit together. Any questions on that formation there? Yeah. It will move backwards, right? Yeah, because it lost. If it gains, it goes forward. Yeah. So that's what we see here. So typically our nonmetals, as we just talked about, the guys are going to gain electrons. So when we look at a metal, nonmetal, when it comes together, and we look at the nonmetal, we should see the nonmetal end up at the noble gas that comes right after it on the periodic table. So if we look at fluorine, the noble gas right after is neon. So it gains that electron to do that. Our metals, as we talked about with the periodic trend, are typically guys that will lose electrons. So they do end up backing up to the noble gas that comes right before them. So if we look at lithium, the noble gas comes right before is helium, and that's why it backs up to that guy. Yep. Other questions? All right, so let's take a look at another example here in just a second. But again, what really is holding that together, as I talked about, again, is no sharing of electrons. The electrostatic attraction between the positive and negative is basically holding that unit together. I think we talked about it a little bit earlier as well. There is sort of increased strength as well when you take the charges. So higher positive charge, higher negative charge is held together tighter than something like +1 and -1 versus +3 and -3. You know, they are held together tighter. An ionic bond is the bond that holds an ionic compound together. It is always 100% a safe bet. If you see yourself with a metal and non-metal come together, that is an ionic bond, no matter what the deal is. It's pretty much the deal. This is what's going to happen. You're going to have a transfer of electrons from the metal to the non-metal, creating two ions that are held together by that opposite charge. When we look at calcium oxide, for example, calcium is group number 2, which means it should have 2 valence electrons. It also starts with an electron configuration as we've written before, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It then comes together with oxygen, which is group number 6, which means it has 6 valence electrons. And 1s2, 2s2, 2p4 in terms of its configuration. What's going to happen here is calcium, if it lays up 1 electron, does calcium end up at a noble gas configuration in this case? It does not. If it just gave away 1 electron, it would back up just 1 spot on the periodic table and put it at potassium. So calcium, because it has those 2 valence electrons, will give away both valence electrons to oxygen. The result of that is calcium has now lost 2 electrons and becomes positively 2 charged. The oxygen will gain those 2 electrons and become negatively 2 charged. Again, the bond between the +2 and the -2 is what's holding that together. What happens in terms of our electron configuration is very simple. Our calcium will lose these 2 electrons, leaving it as 1s2, 2s2, 2p6, 3s2, 3p6. That is argon's configuration, 18 of them. Yes, so we should have went backwards. Oxygen will put those 2 electrons right there in the p subshell as it has room for it. And that will end up with oxygen becoming 1s2, 2s2, 2p6, which is 10, and ends up at neon's configuration. Again here, by losing and gaining electrons in an ionic bond, both elements are able to achieve noble gas configuration, which ultimately is the goal of every single point of bonding, is to get everybody to that sort of configuration. Question on that there? Yeah. So it has to do, so the increase of an ionic bond, if that's your question, the increase of ionic bond, basically the strength of it increases with sort of the numbers. And it's really related to what we just talked about too with periodic trends and size. If something, for example, has a +4 charge, right? It pretty much just shrunk, right? A lot, gave away a lot of his electrons. It's a much smaller guy, right? And then you have this guy now that gained those 4 electrons on the other side, which is much larger. It's like a bigger magnet, if you will. It's going to squeeze it in a lot tighter and hold them together a lot stronger than if they both just kind of drop like one. You know, it's not as big of an overall change. You know, it's not held as tightly. It's still going to be held really strongly, but in relationship to, you know, one that lost a lot of electrons versus one that gained a lot, you can think of it like a magnet, right? You can have this really big magnet, it's just going to grab that really small thing and it's going to hold it really tighter than you had maybe like a same size magnets, you know, kind of, they're not going to be as tight and stuff like that. So that's what we're talking about in terms of that, in terms of the strength of the ionic bond, typically will increase with increasing charge that happens. Yeah, so remember the reactivity is what's going to create the charges, right? So remember, everything on the periodic table doesn't have a charge to begin with, right? So as you go left and down, they're going to be more apt to give away those electrons, which is going to make them more reactive than, again, if you went up and to the right, those guys are going to be a much smaller. Up in a group, in the same group, is going to be not as reactive because of that. So the important part is we're talking about here sort of the end result of the electrons being transferred is that charge, right? Before it starts, they're in a situation where they're going to be more apt to either gain or lose electrons or maybe share electrons, but they're going to be more apt to kind of either be willing to give away those electrons or gain those electrons. And the result of that is you're going to create two things that, in terms of ionic bonds, going to have a certain charge associated with it that's going to create either, you know, regardless of what the charge is, +1, -1, or +4, -4, an ionic bond is a super strong attraction just to begin with, regardless of the number of it compared to any other type of bonding. It's like the strongest you can almost get is like the electrostatic coming together of those charges. But there's a sort of degrees of how strong, you know, you could get with it. Other questions? Okay. So we saw calcium, we saw lithium kind of come together and make an ionic bond. But what happens if we kind of put together two of those guys we just looked at? We take calcium, which is our 2 valence electrons, and we decide, hey, we'll put it together with our fluorine that has 7 valence electrons. And again, if we look at our configuration here, we got our argon 4s2, and this we have our 1s2, 2s2, 2p5. All right, so in this particular case, we're going to get our calcium, which we already know wants to really lose its electrons here. So it's going to give away its electron to the fluorine. At this particular point, can the fluorine take any more electrons? It cannot. It's pretty much full. But calcium, as we just talked about, is not going to be happy just laying up 1 electron, right? Because that only gets it to potassium, which means in this case, we need actually not just 1 fluorine to handle this job, but we actually need a second fluorine to basically take the next electron. When we do so, what we end up with is now a calcium that has lost both of its electrons, which is going to make it happy. We end up with one fluorine that basically picked up one electron, I'll just circle it, and became -1 charge. And we actually ended up with a second fluorine that picked up one more electron and became -1 charge. So in this particular case, in order to allow calcium really to reach noble gas configuration, we actually needed 2 fluorines to sort of handle that. And the result of this is this calcium here was able to end up losing both electrons. So it became the same electron configuration as argon. Each of the individual fluorines actually only needed 1 electron each, right? Which is what they both picked up. And that moved both of these guys, I'll just kind of go like this, both of these guys ended up in the same electron configuration as neon. So in this case, with the calcium losing 2 electrons, 1 to each fluorine, it allowed all 3 of those guys to reach noble gas configuration and be very stable in that particular case. And it is balanced out in terms of charge, right? +2 is balanced out with -1 and -1. I think we talked about this at the end of one of the chapters when we talked about ionic compounds. And whenever we put something that is positively charged and negatively charged together, overall charge needs to equal 0. And that's why when we look at the formula for calcium fluoride, it is a +2 and a -1, which means we did need 2 of those guys to balance out the charge to give us the proper formula. And that is really the reason why when we write formulas for ionic compounds, all the positive charges, the negative charges need to equal 0. The reason for that is actually the bonding part of it. The reason for that is when we do that in the simplest way to get everybody to 0, positive, negative charges when we put them together, that will allow everybody to get to noble gas configuration. So that is why when we put an anion and cation in terms of an ionic formula together, charge always needs to equal 0. Simplest way to do that will allow everybody basically to reach noble gas configuration. And that's really the purpose of what we talked about, I think, just a little bit in an earlier chapter of if you have a positive guy, negative guy, you want to equal 0 in terms of the charge. Question on that there. Question on ionic compounds. That is essentially what we're talking about here. Okay, we're going to lay it up here for now, I think.